Now, this is the second part. This is the cathodic protection section 2. And it will be another section, which should be the section 3, which is the impressed current analysis. And in this section, what we are doing is we'll basically go for a design of a cathodic protection system with sacrificial anodes. As we review in the introduction or in the basics of cathodic protection, an anode needs to corrode uniformly to protect the cathode. The intention of the cathodic protection is to make the intended structure to be protected to behave as a cathode. Basically, all the surface needs to behave as one cathode. The electrochemical cell, for example, we have zinc and the steel. So the electrochemical cell will basically move electrons from the anode to the cathode, like the electrons move from anode to cathode. So the cathode becomes saturated with electrons, and then the ionic flow is basically moved there and reduced at the cathode. It moves from anode to cathode in the electrolyte, or from cathode to anode in the electric pathway. This is the current, and this is the electrons, moving current. This is conventional current. Remember when we reviewed that at the beginning of the course. This is the sacrificial anode. The anode is basically sacrificing to protect the cathode. So this is the basic of the cathodic protection. What it matters when we try to do a design of the system? Well, the size of the anode is very important. And it's important because we need to, at the end, account for the current that the anode can deliver to the cathode. And the size is very important because if the size is big, then more current. Or the surface area. We will see which formulas are being designed to calculate the size or the amount of anodes that we require. It's very important to know the environmental application. It's not the same to design a cathodic sacrificial anode system for the Persian Gulf than for Gulf of Mexico, than North Sea, or for the ground, or depending the electrolyte is completely different because resistivity change. So it's important. So a sacrificial anode system, it requires to know the ohmic resistance is basically what we see. So to calculate the ohmic resistance, we need to apply the Ohm's law to calculate the discharge current. It's very important. The number of anodes is also very important because we can reach the potential that we want to, or reach the potential that we need to protect the steel, and by the number of anodes. And of course, we need to validate this number of anodes. So this is some sort of the algorithm that we need to know. And this algorithm is, we will review the algorithm, we will review the equations, we will basically stress which equations we need to use at which and when, which moment, and which numbers do we need to include in the example. And basically this will be your final review because you just need to fill this procedure in Excel calculation and hand out or send it by email, and it will be basically your next assignment. So the resistance calculation, or the resistance calculation, it requires different parameters, but there are basically 4 equations that are being developed to calculate the resistance of the electrolyte. So the first one is the Dwight equation. This is for anodes with shapes of bars or slim anodes. Then we have McCoy equation, which is designated to evaluate the exposed surface without considering the shape. This basically just taking the surface. And then we have the Peterson equation, or Waldron and Peterson, that is very similar to the McCoy equation, but the results differ. And at the end we have Lloyd's. Lloyd's equation is a simplification of the Dwight equation. So when we talk about the Dwight equations, the Dwight equation is an anode with shape of bars or slim anodes, and this is the equation that we need to know. So the equation that basically, that equation there for anodes that are with a length higher than 4R. L is the length, rho is the seawater resistivity. Now this is the seawater resistivity, but we can apply then the soil resistivity or any other liquid resistivity. And the small r there is the effective anode radius. So now for short, this is for long, like long anodes, and for short anodes is basically apply the second equation. In the example that we are planning to use, we will use the first one. We will use this equation to calculate, assuming the stuff that we want. The McCoy equation is designated to evaluate the exposed surface without considering the shape. So it's basically just evaluating the exposed surface area. So this equation is used when one face of the anode is in direct contact with the structure. So it's basically a bracelet in the pipeline, or anode touching a ship, or in the platform, it's an anode touching the structure of the platform. This is the McCoy equation. It's very similar to the Waldron and Peterson. If you see the equation, it basically follows similar variables, but the resistance changed completely. So the Peterson resistance is like McCoy, is a function of the anode surface area exposed to the electrolyte. But the results differ completely. The resistance are completely different, and then you can calculate by the sake of seeing how it changed, but that's important to have it.